Together with him are four distinguished guest speakers, Professor Edward Witham, Professor Kiran Vaffa, Professor Hiroshi Kyukuri, and Professor Anton Kapustin. Let's give them a warm welcome.
Okay, so welcome everyone. It's a great pleasure today to have top experts in theoretical fundamental physics here with us, and for this top talk. And since the topic will be physics or fundamental physics in the 21st century, let me start maybe with the first question about the future. So. Maybe I start with Professor Oguri. What do you expect to be the major fields in the coming decade? Say, right now, in theoretical physics, we have people are working on the major fields of quantum information, on dualities in string theory and quantum field theory, in topological symmetries, and also on cosmology and particle physics. So these are all distinct fields with relations, and there are also communications between them. But maybe what is the near future? What is the expectation for that? What will be more important?
Okay, the first answer to your question is that if I knew what that would be, then I would not tell you, but I will just work on it. But this is actually a good time to be asked this question, because at the Strings conference this year at CERN, which is the largest conference of string in our field, Andy Strominger and I were asked to give concluding remarks. So we actually solicited the questions that are sort of achievable, solvable in the next 10 years, and we got 100 questions. So we discussed these questions. And I think that one of the very interesting directions that, at least in my area of science, can contribute is to connect the different areas of mathematics. Because what we are doing is to push the boundary of human knowledge, to try to unify general relativity and quantum mechanics, and we are expanding our knowledge of human in the most microscopic level to the beginning of the universe that we have not been. And in order to explore such a regime, we need to develop new mathematics. Just like Isaac Newton developed calculus to formulate classical mechanics. We need new mathematics, and that requires combining different branches of mathematics, analysis, the geometry and the algebras. And so that is an area where we can make impact. In my perspective, I think I'm not a mathematician, and but what I would like to do is to formulate the kind of question that, and also the statement we make in theoretical physics as precisely as possible in the mathematical language, so that the mathematician can think of that as a conjecture and try to solve that. Yeah, so I think there are lots of these interdisciplinary areas that we can explore in coming area. And I can tell you more specific about it, but I shouldn't be speaking too long, so I should give it the stage to other speakers.
Okay, Professor Witten, maybe your input on this?
Well, as Hiroshi said, if I knew what was the areas where there will be greatest progress, I would know what to work on. And knowing what to work on is always the most difficult part of research. So regrettably, we don't. And looking back at previous periods, I can see that if asked such questions 10, 20, 30, or 40 years ago, I would have been wrong most of the time. With that said, I'll venture a couple answers, presumably not necessarily answers likely to hold up too well. One is that there are so many clues about the relation between gravity and quantum mechanics unearthed in the last decade or so that I hope there might be some general insight emerging about what it all means in the next 10 or 20 years. A second hope is that in string theory, I'll state it both narrowly and broadly. Narrowly, we don't have much understanding of string theory with strong time dependence, and we might make progress there. More broadly, again, in string theory, there's an incredible web of things that are known, but little insight about what it all means. And you can always dream. Thank you.
Thank you. Professor Waffa?
Thank you. Both Hiroshi and Ed said something I would also like to add, that we don't, of course, know where we are heading. I could only maybe change the version of the question that I can say something about, which is what I wish will happen, which is what we are striving towards. So as I mentioned, one of the main things I want to understand is what are we doing with quantum gravity? What have we learned, and what is the analog of the laws of quantum gravity in some form? So we have gotten pieces of it, like we have learned holography is an important piece of quantum gravity. We have learned a few other pieces of it, like dualities. And they seem to be all true in some form, but we haven't been able to say, okay, quantum gravity means this. Like in the context of Maxwell's equations, we know what they are, and that will describe all the electric and magnetic phenomena, and we want the analog of that way of formulating string theory as to what are the principles exactly, and which everything else follows. We are not there yet. So that's one thing I want to wish we get to. More concretely, in terms of specific applications to our universe, I would be certainly very interested in understanding the nature of dark energy. This is one of the main puzzles we have in our universe, the energy that is everywhere and is so small, nevertheless. And the surprising thing about this energy is that it is positive. If it were negative, we had a lot of good models for it. But when it is positive, just a sign of it gives us a headache in understanding it in the context of string theory, or probably more generally quantum gravity. And that is a major puzzle because we live in such a universe. And so that's one of the big hints we have about our universe, is this positivity of energy. We do not have reliable constructions in string theory which gives you quasi-static or almost static positive energy. Understanding how this can come about or cannot come about, or what are the features, could be a big hint about how our universe works and how to get predictions from string theory.
Yeah, thank you. Professor Kapustin, what is your opinion?
First, in my own narrow area, I think I really hope for more thorough mathematical understanding of high-energy physics and elementary particle physics. So I think without solid mathematical base, if you cannot formulate something in a mathematically consistent way, you don't really fully understand it. And I think that's a job for both physicists and mathematicians to finally figure out how to put elementary particle physics on a solid mathematical basis. And I think that's a matter of, it's maybe not that hard. That's progress can be made in the next decade or two. And more far afield, I think quantum information science is a very exciting area. And I've seen a lot of progress being made in, say, solid-state physics using the ideas of quantum information. And I look forward to even more exciting developments. And if I wanted to fantasize a little bit, maybe even cognitive science would have an important works. Cognitive science is also about, and maybe if you use cognitive science, we can understand parts of our knowledge are really subjective and which parts are really about the physical world.
Thank you. Yeah, maybe since almost all of you mentioned mathematics and important developments of mathematics, I want to go back to you, Professor Oguri. Which branches of mathematics do you think will be more important or will be needed for the current development?
Well, that's a difficult question to answer, because very often what happens in physics is that unexpected branch of mathematics turned out to be useful. So I've actually what I look for is to learn new mathematics, and but I think in that respect, actually, one of the interesting developments that could happen in next 10 years is the more extensive use of AI and machine learning. And so I was curious to know what will be the impact of AI and machine learning to theoretical physics? And of course, the first thing I did was to ask ChatGPT that question. And it gave actually a very good answer to my question. And actually, there is a long answer to the question, but there is one very interesting answer, which is about theoretical insight. Machine learning algorithm can help uncover new theoretical insight by identifying hidden correlations and structure in existing data, potentially leading to new hypotheses or refinement of existing theories. And this is actually a kind of things mathematics do too. Namely that mathematics is find structure in nature, that, or maybe more Platonic world of nature, that to look at the new structure. And so I think that the use of machine learning can help us do that more. And the interesting thing about this technology is that this might tell us new connections that we have not known before. So, in fact, if I may say expand a little bit more, so since there are a lot of young people, I would like to recall when I was in high school. So when I was in high school, one of the science books that gave me most impact, one of the most impact was a book by Henri Poincaré, the famous mathematician. It's called Science and Method. And in the last chapter of the book, he asked himself, what is the important direction of science that one can study? This is an important question. That's the kind of question we are talking about today. And he answered that question. So I read that part very carefully. And what he said was that you should work on the program that has impact on broad area of science. That he pointed out that there is an area of kind of questions that program that you work on, and you only solve that problem, no impact at all. No, you should work on the program that sort of change the perspective and give impact to broad area. And I think precisely formulated mathematical statement can have such feature. Thank you very much.
Yeah, thanks a lot for this inspiring answer. I think this will give us all some food for thought, but that also brings me immediately to the next question, namely, you basically went out of the box and ask new questions, and that is exactly what I wanted to ask next. What are the themes we have been missing, or what would be actually very important to work on, but not so many people have been paying attention to it? So what are the missed opportunities? Have we been missing something? And I think you mentioned some part of it, and I would like to ask Professor Kapustin whether you have also some input on that.
Sure. I alluded to such a subject indirectly in my previous answer. So to understand elementary particle theory, we need to learn quantum field theory. But when you ask a mathematician, like, what is quantum field theory, they usually would tell you that they cannot tell because it's just not mathematically rigorous. And I think this is the area making quantum field theory a mathematically rigorous subject, which should be a focus of attention of many more people than it is now. Some people are working on it, but it would benefit from more attention from both physicists and mathematicians. And I would also say that the situation is a bit embarrassing in that respect, because quantum field theory has been, formulated on a physical level in the 1950s. It's been 75 years, and we still don't have mathematical understanding of what quantum field theory is. The last previous situation like that was statistical mechanics. When American physicist Gibbs formulated statistical mechanics around 1900, it took around 50 years to formulate it mathematically using measure theory. But now we have 75 years of no mathematical theory of quantum field theory. That's really embarrassing. So I encourage everybody to work on this problem.
Yeah, thank you. Regarding research on quantum field theory and aspects related to it, I think there are different areas and people are working on from different angles. Say quantum information is one major branch which is very active these days. And on the other hand, there are questions related to dualities in quantum field theory and string theory, or dualities inspired by quantum field theory and string theory. And it seems that there is some communication, but largely these fields are kind of progressing independently. And I wanted to ask Professor Witten whether you expect that there will be more interaction or unification that we can see in the future.
Well, hopefully some areas that aren't so well connected now will make more contact. What I find most striking is that I see two areas that are of greatest interest to me where a general insight is really needed. One, I kind of mentioned them before. One involves this connection of gravity and quantum information theory, and the other involves the question of learning a general lesson from string theory. String theory is some new kind of geometry, but we don't at bottom understand what it is. And we've learned many new things about string theory in the last 30 or 40 years, but there are some basic mysteries there where our understanding is as primitive as it was before. So hopefully we'd make some progress there by unifying some directions we don't now unify or something, but I'm afraid I can't shed much light.
Professor Waffa, maybe you have some input on that?
Maybe related to some of the topics that came up. I think one theme in the development of string theory in the past 30, 40 years has been not single directions, but unifications of ideas. And dualities is an example of it. So related to that, when we say which area of mathematics might show up and which area and so forth, one thing we learned in string theory is not one area of mathematics. All of mathematics come together, and not just in different parts of physics. Even for the same problem, for the same physical problem you're studying, many, many different aspects of mathematics comes in. And so the idea of focusing on one thing may not give you a deep insight. And the deep insight comes precisely from the synthesis of different ideas put together. Duality is basically capturing that idea that you should not be having a single viewpoint on the subject, but multitude of viewpoints. So if you ask me one of the main lessons we have learned in the context of string theory, is precisely the idea that we should bring diverse looking ideas which are unrelated a priori and put them together. So the ideas that may propel us in the future is to be broad-minded, somewhat similar to what Hiroshi was mentioning about Poincaré's suggestion having major impact, but maybe in the reverse form, absorbing major impact from all these different fields and bring them together into one kind of applications in different problems. So in terms of retooling and methods and so forth that we need to learn, I would say that we should be cognizant of not just the traditional areas that we are familiar with, but broadening them as much as we can, as we have learned that it is not a single viewpoint that's successful in making us understand what is going on, and to be open to bring diverse set of ideas together and bear it on physical problems we want to advance.
Professor Oguri, maybe some input on relations between different fields?
Well, yeah, so actually listening to especially Professor Kapustin's comment, it came to my mind that even though I deferred, I hesitated to point out particularly interesting direction, but one of the direction of mathematics which I think in the long term, maybe next 10 or 20 years, I hope would be more developed, is to develop the technique of dealing with analysis and calculus of infinite dimensional space. Because, so as I said, calculus was developed by Newton to describe classical mechanics. And one of the difficulty in dealing with quantum mechanics is we have to deal with infinite degrees of freedom. And there are new structures and mathematics coming from dealing with such questions. And as Professor Kapustin said, that in the last 10 years or so, there has been actually a lot of new insight and surprises coming out from analysis or in such a direction. And quantum field theory can both help and be helped by developing such mathematics, because for some statement of quantum field theory, we know, even though we cannot prove to be true. And that can be a guidance in developing such mathematics.
Yeah, thank you. Any other comments, Professor Kapustin, about possible unifications of existing kind of directions?
Well, I just wanted to comment on the relation between math and physics. Is that of course, they're very different. And say, I'm a physicist by training, and one lesson I learned is that math, one shouldn't be afraid of math. Math is amazing, and physicists should use all the tools available, and math has the tools to solve real physical questions. So lots of physicists have that attitude. Well, it's abstruse math, maybe I shouldn't learn it, it's just scary. Don't be afraid, it's not as scary as it looks, and can be tremendously rewarding. So, and second is that, of course, nevertheless, one shouldn't be like too fascinated with the math formalism if you're in physics.
It's very hard to predict. But one of the things that are already emerging is what I mentioned. One of the things I mentioned, which is that its ability to connect different things in an unexpected way and bring in new ideas. And even some phenomena called hallucination can be useful in that respect. On the other hand, so far AI has not been so good at sort of rigorous and precise logical argument. That can change in the next few years. It's hard to know. But so far, but on the other hand, generating some interesting ideas, the random ideas, some of them can be interesting. It seems like it can be very useful. But as I said, it's very hard to know. My hope is that its role will be complementary to humans. That it will, just like, for example, the calculators and mathematicals and other tools, did not replace human, but help us make advance in science. And AI could play such complementary role. That would be my hope. But we never know. Maybe we're going to be replaced by them.
Okay, so you think that we basically the AI will help us to maybe come up with new solutions to problems, but also to connect different areas.
Yeah, that already seems to be happening to some extent. Mm-hmm. Yes.
That's very
identifying patterns, for example. So for example, if you give AI certain data, it can tell you that there is this pattern, and then we can go on and then actually make rigorous argument to do that, and that has already been quite useful in my view.
Mm-hmm. So the role of the human is still hopefully useful in the future. And also I wanted to ask Professor Waffa what your input is on AI and the role of humans in the research.
Yes. I think the lesson of history of science shows that our view of nature has changed in a way that suggests that we are not at the center of everything. More and more and more. I mean, the history of, we are the Earth or as the center of the universe was revolutionized already many centuries ago. We know that's not true. The evolution casts doubt that we are much different from animals. We have evolved from more or less the same structure, so we are not unique. And now we are faced with the last uniqueness of ours, at least on the planet Earth, which is our intelligence, we think, is unique, at least supreme, compared to other species. And now it's being questioned by what we have already beginning to develop ourselves as human beings, namely the AI. So I think it is a difficult period for humans. We might feel a depression as a species, where one of the last vestiges of our advantage, we think, relative to species, might be replaced by our own construction. And I do not know what to think of that. It's not a question of whether I like it or not. Whether it will happen or not is not up to me. I think it will happen in some form. The question of whether or not we are going to play a major role in it, again, as being helpful to whatever that new way of advancing is unclear to me. I think we should be embracing but somehow understand what's going on. There are, of course, dangers of this new methodology, which again is something to be cognizant. It would happen not just through the science, but its applications that could be dangerous as well. But we have to kind of move in that direction, because it will happen regardless of whether we are helping it or not. It will happen maybe slower or faster, but it's going to happen. And see what will happen. So I think we should be open-minded. And we should not be too shocked, in my view, if we use our central location central position of running the future of science.
Thank you. Yeah, I hope this is not too worrisome, but that there will be some bright spots also. But let me also ask Professor Witten what your take is on this.
Well, my main comment is that I would certainly look forward to the opportunity to discuss physics with a machine that was interested and capable of having an interesting discussion about physics.
Okay, that's great. Yeah, that will be certainly fun, and I hope we can all experience that. And maybe regarding another aspect of technology, addressing Professor Kapustin, what about quantum computation? Do you see that there will be major breakthroughs, and if so, what will be used for making progress in fundamental physics?
Well, that's a difficult question because it's not my area, so I cannot really say much about quantum computation itself. I just think that for physics application, it would be great to have a general-purpose quantum computer which would be able to simulate quantum systems which are currently beyond the reach of theorists, and there are many such cases. And in particular, if one could say shed some light on some famous unsolved problems using a quantum simulator, like high temperature superconductivity or something like that, that would be great.
Professor Oguri?
Yeah, again, well, it depends on what the question is. If it is about experimental science, I have very little to say, and therefore, in terms of near future application of quantum information technology in solving actual problem, I have very little to say, except that, originally Feynman was proposing quantum computation to actually simulate quantum system. So in that area, probably there will be a near-term impact. On the other hand, the study of these technologies and also quantum information theory have already had impact in basic sciences. And I think that some of the new mathematical tools that have been developed in that area are having broad application even. For example, study of holography and relation to quantum error correcting code. For example, during this conference, I was honored to receive an award, the Frontier of the Science Award, and that was given to my paper where we used the quantum error correcting property of holography to prove some theorem in quantum gravity. So I think these mathematical techniques have been very useful already.
Maybe let me also reformulate and ask the other way around. Do you think that there will be impact of fundamental physics, new developments in fundamental physics on progress in quantum computation?
Yeah, well, we have already also seen in that direction because it's sort of dual to each other.
Right.
That I'm using technique idea of quantum information to understand quantum gravity. But for example, a famous example is that the idea of wormhole through black hole has been used to develop some new protocol for quantum error correcting code, not quantum error correcting code, but quantum teleportation, that to send information quantum mechanically. And some people are using the idea of black hole and wormhole to develop new protocol for that. So I think there are lots of ideas going between them.
Professor Waffa, maybe?
I mean, quantum information, quantum computers will impact whatever we do, not just in science and everything, presumably. But from what I understand, and again, this is like the others already mentioned, it's not my field, so I'm only saying from the information I receive from more experts. For example, my son is studying this field, and when I talk with him, the idea I get is quantum ideas of quantum computers. Even if there are two aspects. One is realization of them physically, and the other one is what does it do after it's physically realized. So let me aside the physical realization, which is going in some speed, but not super fast. It's going there. But even after it's realized, from what I understand, people who are actually working on these topics give the information that they are not necessarily much better than the classical computers for most problems anyhow. So they might be good in some problems, like an example that Hiroshi mentioned, for example, for quantum systems itself, they might have advantage. But I think by and large, there are going to be specific questions they might be good for, but not for every question necessarily until we have a much scaled up version of them, which is not in the near future anyhow.
Professor Witten, any comments?
Well, one thing that quantum computers are certainly good for is demonstrating that quantum mechanics works in much more complex situations than it was ever tested traditionally. That's already begun to happen, I think.
Yeah, that's certainly very interesting. Maybe let me also come back to a comment you made, Professor Kapustin, about possible important research directions to which fundamental physics can contribute, namely, you mentioned the question of consciousness. Do you think that any of these new developments also in physics combined with quantum computation and AI will have impacts on that direction?
Again, that's something not my area, but I rather hope that the flow of ideas may be from in the other direction. So maybe it's, for example, quantum mechanics itself is not well understood. In particular, the famous Copenhagen interpretation has been criticized as being not completely consistent or maybe subjective, and perhaps ideas from cognitive science could actually help us understand what quantum mechanics is really about, because much of it is formulated in terms of knowledge of observers, that is people, and seems a bit strange to talk about this in the context of such as science as physics. So I would expect maybe some ideas from cognitive science to help resolve this paradox.
Professor Oguri?
Yeah, so, well, as a scientist, it's kind of difficult to try to talk about subjects that I'm not the expert of. But first of all, what I would like to say is that in order to discuss this kind of issue, you're asking consciousness. Scientifically, you need a definition. You need a mathematical definition of what you're talking about, and I think that's lacking. But even if you don't talk about it, we can try to see whether there are ways that we can try to develop mathematics to understand artificial intelligence better. So I think we have been very good at formulating and understanding emerging phenomena. So for example, in condensed matter physics, in the microscopic level, you have atoms and electrons. But then we can describe this phenomena in a sort of a collective mode. And then there is an emergent phenomena. And it is likely that the experience we have in our brain is some kind of emergent phenomena. And so I think so again, this may have to do with dealing with a large number of degrees of freedom, and developing proper mathematics can be helpful. But I think we also need a definition on the subject.
Right, that's very true, yeah. Comments, Professor Waffa?
I think the notion of consciousness is as mentioned, is not quite well defined, at least not to me. And if you ask the analog of the ChatGPT, are you conscious? It might say, yes, I am. And so depends on definition. So I don't think it may be a well-defined thing. It could be like a gradual more and more conscious. Like when we are dreaming, are you conscious? Well, partly, maybe a little bit, maybe not. And so is there a sharply defined object, or is it some gradual transition, like emergent, as Hiroshi was referring to? So I don't think it's important. Perhaps not unrelated to that, maybe combining the last two topics, is whether or not consciousness and quantum aspects are connected. Maybe that would be a question. And I mean, people have described, for example, whether or not our mind is quantum, and consensus it's not, even though people have raised the other possibilities would have been far more interesting if it were. But it seems like we don't have much evidence of that. But it would be interesting to see if there is any aspect of quantum within us that is crucial in thinking. And so far, we don't have much evidence of that. So,
Professor Witten, any comments?
My main comment is on how the impact might be on society. Because it would seem likely that in the 21st century, well, many people, at least in Western countries, I'm less familiar with attitudes in China or elsewhere in Asia, for example, have the concept of a soul that's distinct from the body. And I think that it's very likely that in this century, developments in both neuroscience and computer science will call such views into question. It'll be more and more clear that a machine can behave in a way that one would intuitively think of as being conscious, and meanwhile, developments in neuroscience will possibly, I don't know if I want to say demystify, but clarify what's going on in our brains. So I would expect that those might be two of the areas of science with the biggest impact on society in the 21st century.
Mm-hmm. Yeah, thank you. So, as you mentioned before, that there would be fun to have this machine with whom to be able to have a physics conversation, and I assume that would be one example of exactly that kind of change in the society.
I've tried. So, for example, I chatted with Claude, which is created by the Anthropic company and is currently said to be the best AI system, about the nature of quantum mechanics. Actually, I tried to have a discussion about the papers of Hugh Everett on the foundations of quantum mechanics. It didn't work well in the following sense. The first iteration, I got what I'd call a trivial answer. Then I questioned the trivial answer, and I got a slightly better answer. And we went through many rounds of this. And at the end, Claude was more or less arriving at the point I tried to make the discussion start at. So I did not have a happy experience when I tried to discuss the foundations of quantum mechanics with Claude. And to save time, I won't tell you about other experiences, but I've had a few other similar experiences.
I see. Yeah, so the machines are not there yet, but maybe will be better in a few years. Let me come back to the our actual field, namely fundamental physics, and address experimental questions. So, what do you think will be the area where experiments in the near future will be able to actually confirm say, string theory or aspects of string theory or other theories which are important but not yet experimentally verified? I mean, Professor Waffa, maybe you have any comments?
Yes, high-energy physics is the area where we try to connect to fundamental physics, and high-energy experiments is the source of a lot of our current understanding, for example, of the Standard Model. All has been developed through what we have found in the collider physics in particular and many other things. So it is natural to expect a continuation of this process. Now, the rate of discovery of new features has slowed down for some reason in some ways in the particle physics domain. The last discovery was, the last major discovery, I should say, was the Higgs discovery, which was anticipated for many decades already. So it wasn't adding new knowledge, but confirming what we were expecting, except finding more precise values for the masses and things that we didn't know. But actually, I expect that this trend to actually change in the context of fundamental physics in the near future. And I think there are hints in how this is going to change. It may not be directly from accelerator physics. It may not be directly from the traditional part, but I suspect a lot of it will come potentially from combination of particle physics and cosmology and precision measurements in some form. And for example, as I mentioned just before, the notion of the dark energy, that there's this positive energy, small positive energy everywhere in the universe, is one of our major puzzles. Ideas in string theory suggest that this cannot be absolutely stable. Now, whether it's gradually unstable, in other words, gradually changing, or jump suddenly and so forth, something we do not know in string theory. But observations of dark energy and its nature is one of the key questions also in the context of cosmology today. And there are preliminary experiments which are hinting that it may not be constant, for example, and there are ongoing further experiments to see what they are. So I think the nature of dark energy and its features, whether it changes or not, I think is one of the things that's going to help us formulate its connection with fundamental physics. Other things, precision measurements, there are a few ideas from string theory, again, string dualities, which suggest the smallness of this dark energy may be related to the existence of one extra dimension which is larger than the others. And this idea, if it's true, this dark dimension would suggest that something you could actually measure in near future experiments, maybe within the decade even, of, for example, finding the force of Newton, gravitational force of Newton, which is 1 over r squared as a function of distance, to change and become 1 over r cubed because we have one extra dimension at smaller distances. And if we see the strengthening of the gravitational force at shorter distances in a way consistent with that, it potentially could be exciting. Again, this is again related to dark energy because the scale in which this is happening is close to the scale suggested by the dark energy, which is around the micron scale or slightly more. So these are the ideas that I think are there. Now, on top of this, we have questions having to do with the axions. The QCD axion are expected to exist, and we expect them in the next series of experiments that are already taking place. It could very well be that we discover the QCD axion. So that's one of the major puzzles that we still don't have. We haven't had a deeper understanding. And finally, the neutrino sector is another part of particle physics, which still occasionally we hear anomalies which go and come and disappear and so forth, but it's still some of the, we feel, they give a hint as beyond the standard model questions. So I think on better understanding of the neutrino sector, axionic physics, dark energy, its nature and its changing, and these precision measurements, and possibly the electric dipole moment of the neutron and so on that people are measuring. These different experiments all are going to push towards more fundamental questions in physics and potentially to fundamental ideas within string theory and string dualities.
Yeah, thank you. These are certainly very major questions. And what is your take, Professor Oguri, on possible...
Professor Whitten was also holding
okay.
mic, but well, Professor Buffer is a chair of the physics department, so he hit all the areas, obviously. But one area that I also wanted to mention is the early universe. And so if you go to early universe, Big Bang and earlier, universe was denser and high temperature. So this is a natural area to look at physics that goes beyond the standard model of particle physics. We understand the beginning of the universe after 10 to the minus 10 seconds, roughly speaking, if I remember it correctly, after the beginning of the universe, because in that time, we can still use the standard model of particle physics, and we can test the various predictions. But if you want to go earlier than 10 to the minus 10 seconds, then we don't have theory. So if we can make observation of the universe earlier than 10 to the 10 seconds, then we can test theories. For example, there is the model of inflation, inflationary cosmology, where there is a hypothesis that the universe expanded exponentially driven by some scalar field potential. And that's supposed to describe the universe from the beginning, the 10 to the minus 35 or so after the beginning of the universe. And you can see that that will be way beyond the current standard model of particle physics. And so this is the interesting area to explore. And now there is actually, within the next decade, there are lots of experiments that are going to explore that area. CMBS4 in the United States is one of them. Unfortunately, there is some kind of issue with the South Pole Station right now, but I hope it will be resolved. In Japan, at IPMU, which I was the director of until last year, is collaborating with the Japanese aerospace agency to launch satellite in the next 5 or 6 years to measure the polarization of cosmic microwave background radiation. And that, if we detect it, that can give us a hint of whether inflation scenario worked or not, because it tells you about the primordial gravitational waves. In fact, Caltech and other universities tried to do that about 10 years ago, and this was a false signal. But at that time, it was very exciting, because it turns out that they thought they detected the signal much bigger than expected. What is called tensor scalar ratio was 0.2, I think you remember. And at that time, I was actually deputy dean of physics and mathematics and astronomy at Caltech. And since Caltech was involved in it, so we heard about this news like a month earlier. So one day I was working in the dean's office, and the dean came in and said, you know, the bicep detected the polarization of CMB. And I said, how much? And he said, 0.2. And I said, great, it's going to kill string theory. And it didn't happen, but you see that this type of measurement can have impact in fundamental sciences.
Yeah, thank you. Professor Witten?
Well, one comment is that I certainly hope we'll persevere in going to higher energies with accelerators. Of course, if we do, we don't know what we'll find, but that's the nature of science. In exploration, you never know what you're going to find. But there's definitely a possibility of discovering a very fundamental new level of clues about the basics, laws of nature. And incidentally, plans for such future accelerators are very actively developed in China, among other countries. So it's conceivable that this is an area where China will play an important role in the future. As for other areas, there are various possibilities, but one I personally am quite interested in is the possibility of detecting ultralight particles, loosely axions, as suggested by string theory models.
Yes?
Maybe I should add, I also highly second the statement Ed made about going to higher energies. They are unknown, so I think that the idea of trying to push the frontier of energies, regardless of whether we get new particles or not, is necessary. I think the approach that the potential experiment here in China might take place is quite exciting, and I think if it happens, it's going to have a major impact in many things. And usually when you do something new, you don't know where you end up, so I think we should certainly push it if it's possible at all to get it, regardless of whether we think our theories give you such a prediction. So I think today's theories do not have a specific prediction in this range, which is in a consensus way, but that's the nature of science, and I think pushing the frontiers of energy, of course, is always useful.
Yeah, certainly the case that if you push energy higher, there have been new discoveries. That has been the history of science so far. And in the range that the next accelerator is looking, certainly, for example, one of the very interesting things to look at would be the nature of Higgs interactions. That whether Higgs particles are fundamental or composite, and if so, what their interactions are, and if that pattern of the interaction fits with the standard model, or something more exotic. And I think that there can be surprise in that direction, for example.
Okay, yeah, thanks. Professor Kapustin, any comments?
Just a short comment that not that long ago, a new window in the universe was opened by the direct detection of gravitational waves, and perhaps gravitational waves from early universe could provide some tests of fundamental physics. It's a very exciting direction, I think.
Thank you. Yeah, thank you all for these very interesting comments about future connections to experiment. And I think now is a good time to open the discussion to the public and let the young people ask questions, and maybe we get some interesting questions from there.
Thank you, professors, for our really impressive, really cutting-edge presentation and discussion. And it's a pretty good time to open the floor for our young students for your questions, comments, and ideas. So if you have any of this, please raise your hand, and it's your turn. And don't be shy. Okay, let's see who comes first. Okay, you please. Please.
My question is for Professor Vafa, and I want to know, how do you envision the role of string theory in bridging the quantum mechanics and the general relativity in the future, in the upcoming decades? Thank you.
Thank you. So in the context of string theory, we have a unified framework where quantum mechanics and general relativity are put into one framework. So in that sense, we have already achieved that. However, we haven't been able to distill the lessons we have learned from that. So I feel that what we are missing is, after a lot of experience with constructions in string theory of good solutions to string equations, what does it actually mean about the connection between quantum theory and gravity? We have learned through this link that gravity, general relativity, and gravity in the classical sense is very, very different when it has quantum aspects mixed into it. In other words, classical general relativity is a far more, what could I say, far more open situation than actual restrictive setup that quantum aspects imposes on it. So quantum theory puts a lot of more restrictions than we would expect. And understanding this more deeply, why and how does this happen, could give a big hint, because many parameters around us in quantum theories or in standard model physics look very fine-tuned. They look very particularly strange, small or large, and they look like there's no good reason for them to be what they are. And so potentially these high restrictions that quantum consistency of quantum theory places when combined with gravity could shed light on these kind of questions. And I hope better understanding of lessons from string theory could guide us in that direction.
Thank you. It's a really good question. Does anyone else on the panel have like different aspects or something to say about it? Okay, and that's fine. Let's go to the next question. Okay, please, the young lady.
Hello, fellow honored professors. I know that my question might sound a bit trivial, but when I first encountered Newton's laws, I learned that acceleration was caused by force, but at the context of time, they happen simultaneously. So that led me into thinking, what actually is cause and effect relationship? So does acceleration cause force, or does force cause acceleration? And on top of that, I have this really important question, like, what if there isn't just one fundamental truth in physics? What if it's just stemmed from like different points and based on context? In one context, the particles behave according to rule 1, and in the other context, it happens to behave according to rule 2. And that is just as it is. It's not stemming from one, like, point 0. And if the truth is that, and it's not that the entire system of physics or something is built on like one fundamental starting point, but based on multiple fundamental starting points, would that be satisfying, or would that be logically impossible?
Okay, so let me answer your questions. Those are very interesting questions, and thank you for asking that. So you had two questions. One is about Newton's law. So I have a quick answer to that question. I view that as the definition of the force. So in Newton's, if you look at Newton's laws, then they don't have a definition of the force to begin with before he starts telling us the laws. So I view that equation, the acceleration times mass is equal to force, as a definition of the force. And so that's the answer to your question. For the second question, it's a profound question. And it's a mystery. Even Einstein said that it's a mystery that we can understand the nature. And so it's surprising that we can understand how the universe works in a mathematical way, in a coherent way. And the reach of our understanding go much beyond what we are entitled to. And so, for example, the surprise happens about 400 years ago when Galileo Galilei pointed the telescope to the night sky. And then they discovered that moon looked like our Earth. Before that, moon was thought of as a very sort of perfect object, the round and the sphere. But he discovered there are like valleys and mountains in the moon. And so before that, people thought, well, at least Western people thought, that the laws of nature on the earth and the laws of nature in the heavens are different. So that was just like you said. But the discovery hinted the possibility that maybe that the laws of nature are the same here and the heaven. And so if we understand the laws of nature on the earth, then we can understand the universe. And so that was the beginning of the scientific revolution. And that happens the same thing for microscopic distance. You discover new laws like quantum mechanics, but you can extend it. And that's surprising that the human have been able to understand because our brain was not evolved in that way. The brain was developed so that we can have life in a few kilometers. But somehow we managed to acquire this wonderful gift to be able to understand the universe and the microscopic world. That's partly thanks to mathematics. Mathematics gives us a power to explore those. But still, it's surprising that nature is built in such a way, and that's a mystery. Even Einstein didn't understand why it is. But as far as we can explore the universe in that way, I think it's worth doing that.
So I just have a comment on your second question. So your second question, on the face of it, might sound self-contradictory, like is there a truth or no truth or different truths and so on. But there is a sense in which what you said is actually realized already in string theory. So what you say is actually the state of the art today, the way we understand string theory. Namely, we have learned that if you take a physical solution to string theory, there are parameters in your theory. And if you ask what that system describes in a generic parameter, we don't have a good description. However, if you go to extreme limits, then there are simple truths that emerge. You describe, oh, this theory is about this. But if you go a little away from these extreme limits, that description is not the right description. So in some sense, if you're in the middle of the parameter space, there is no, we could say, the truth. That is what we mean by dualities. The string dualities is precisely the notion that there's no classical truth. By classical, I mean something which is simple to describe in what we call the weak coupling description. So something which is simple to explain. Like we say, this is what it is about. So we have learned that indeed some aspects of what you're saying is realized in string theory. There's no simple description. Only in some extreme limits, some simple quote-unquote truths or classical descriptions emerge.
Thank you, professors. It is really provocative and transformative. It let me think a lot. And I hope that maybe in the future, all the series will be like maybe unified or they may have like deeper, or we may have like deeper understanding about the field of physics itself. Anyways, thanks a lot about the answers, and thank you.
Thank you for an amazing question. So let's move on. Okay, how about that one in the 1, 2, 3, 4, 5, 6 row? In the middle. Yeah. Please help me pass the microphone, please.
Hello, honored professors. It is a great pleasure to hear to your discussion. And my question is, to which extent can you agree with a statement? One of the main problems that is to be solved by mathematicians for physics is the notion of path integral, and therefore the main branch of mathematics to be studied is measure theory in infinite dimensional spaces.
I actually, very interesting question, but I actually have two difficulties with it. One is that, first of all, not all quantum field theory can be understood by path integrals, because not every quantum field theory has a classical limit. And it's also true that we're particularly interested in Lorentz signature path integrals, which are fundamentally oscillatory. And even in Euclidean signature, we don't necessarily have positive measures. So traditional measure theory might not be the right framework. But I have a more basic reason to be skeptical about the formulation you offer, which is that I actually don't believe it's true that there's a general theory of infinite dimensional measure theory or infinite dimensional analysis in which quantum field theory should be placed. I think that understanding quantum field theory is how mathematicians will better understand what are the right infinite dimensional versions of analysis and measure theory.
I wanted to add something. So I think I agree that path integral is not something which you should be focusing on if you want to understand mathematically, like say quantum field theory. So in quantum mechanics we already understand, and we don't need path integral for that, even though it's helpful sometimes. And for quantum field theory, the important tools I think will be operator algebras and topology. And that's it's a very promising direction to apply these tools to understand quantum field theory.
Thank you, Professor. Do you satisfy with the answer?
Yes, thank you very much.
Okay. Well, since we are short in time, so we want to have a really quick questions.
I actually want to make one more comment on that.
Oh, please,
Okay,
please.
so understanding quantum field theory with operator algebras definitely sheds some insights and probably more in the future. But it's proved very difficult to actually construct examples that way. And where examples of quantum field theory have been constructed was with path integrals. So to the extent that I didn't completely agree with the questioner, it was because mainly, there were some technical things in what I said, but the main point I was making is that I don't think that one should think of a more general infinite dimensional measure theory with quantum field theory as an example. Rather, understanding what infinite dimensional measure theory should mean will be found by better studying quantum field theory.
Well, thank you. Thank you for your response. So let's welcome the last questions who are going to be the volunteer. Okay, let's welcome the young man in the second line, please.
Oh, hi, I'm an undergraduate student in theoretical physics. Sorry, this question may not be short, but that is the one I really concerned. And I have a question for each of you. Which developments you wish to see in theoretical physics or mathematics over the next 10 years or 20 years? Or maybe we can start with from Babak.
Can you repeat the last part of your question?
All right, so I have a question for each of you. Which developments you wish to see in theoretical physics or mathematics over the next 10 years or 20 years? Or maybe we can start with Babak or Kapstein.
Yeah, thank you for the question. For me, as I mentioned in the beginning, there are these major fields we are focusing on, like quantum information and dualities in quantum field theory, string theory, symmetries, and so on. But they are kind of disconnected, or research on them is progressing in different groups, and I would like to see more interaction and maybe a more unified picture where different people work together on all these aspects and a new phenomenon can emerge. So that is what I would like to see.
I think I already mentioned that I see rigorous justification of quantum field theory. Rigorous formulation of quantum field theory is the most exciting development where physics and mathematics can sort of participate equally, and I'm looking forward to new discoveries in this area.
Yeah, so we already had long discussion on the subject, this panel, but since you asked, rather than giving you my answer in the relatively long term, like 10 or 20 years, for immediate next 5 years or so, what I'd like to understand is a sharp understanding of the prediction of quantum gravity, that what are the implications of unification of general relativity and quantum mechanics in low energy effective theories, and in particular derive those statements from fundamental principle, is something that I would like to spend my effort on the next few years.
It's hard to say what will happen in 10 years. Wish list, if it's a wish list, even though it's not realistic, I would say I would very much want to see quantum gravity understood. That's going to be very unrealistic in the next 10 years, but it's a wish, so I'm allowed to make a wish.
I'm with Kurman. My dream would be that in the next 10 years, we'll get some general insights about the things that we've worked on through our careers, about the underlying meaning of the things we've worked on.
All right, thank you, and thank you all for your contribution to the human science.
Thank you for your questions. Thank you for your response. Thank you all for contribution to this session. It's a really engaging session, but due to time limits, we have to end here. So in this session, we'll talk about physics, talk about quanta, talk about the relationship with mathematics, with AI, with something else. We talk about so many things here, and so happy to have all of our distinguished guests here. Thank you, Mr. Witten. Thank you, Mr. Vafa. Thank you, Mr. Uguri. Thank you, Mr. Kapstein. Thank you, our host, Mr. Hahihat. So let's join join me to give them a final round of applause, please. So, dear professors, you're welcome to go back to your seats. Thank you. Well, the 2024 ICPS Physics Panel in Physics has ended here. So we're gonna have a 5 minute break, and please be returned by 11 o'clock. We're gonna continue our panel and move on to the